All right, guys, hope you're ready for this one. This is really and truly probably the most important video. It is the most important video we've had so far, and it will be one of the most important ones of the whole year for you to understand. So stop it where you need to, take great notes, and if you need to go back and watch it again, please do. You got to get this stuff. Measures of variation. Basically, measures of variation are trying to tell you how far away the data points are from the mean. You know, we talked about sometimes the mean doesn't really mean anything. Like if there's 2.3 kids per family, there's not any families that have 2.3 kids, but we need to know how far away most families are from the mean. You know, that's the important piece of information. So many times how far spread out your data is more important than even what the center of it is. And that's what we're going to be looking at this week, really. Just an example right here. These are Chips Ahoy regular cookies and Triola chips. And you can see that on the dot plot, you know, these are dot plots. This dot plot right here is so much more spread out than this one. Now, if you look at their means, the center's about the same. But the Chips Ahoy, the amount of chocolate chips in each cookie is very much more widespread than the Triola. So that's what we're going to be looking at, is how spread out is the data. One way to do that is by the range. All the range is the max value minus the min value, and that's all you have to do to calculate it. And I put one example down here, and I just did the 170 was the max minus the 40, which is the min, and got 130. Now, one major problem with the range is that it's very sensitive to outliers or extreme values. Therefore, it's really not very useful. I'm not going to use it hardly much at all. Only when I guess we have to, but there's 2 or 3 much better measures than the range, but you do need to know what range is. So there it is. Round off rules, we're going to round off one more decimal place than what's in our data. So if our data, like the last problem, had no decimals, we would go 1 decimal place past that. And we're only going to round in the final answer. Don't ever start rounding in the middle, because if you start rounding in the middle of your calculation, it's going to throw off your final answer also. Okay, here it goes. Gonna do my best job here. You may need to watch it a couple of times because I know how it is. You don't always get stuff the very first time you see it. So here it goes. The word I'm honing in on is something called the variance. And I'm going to try to describe to you what that is. It obviously comes from the word vary. It's how much your data set varies from the mean. So what I did is I drew a little, I don't know, an ellipse, I guess, and put some little data points in there. I put a little bunch of green X's, and I put the mean right in the middle, which is where it usually is. That's our center. And what we're trying to figure out is the blue question right here, which is how far does each data point deviate from the mean? Basically, on average, what is the average deviation or the average variance from the mean? How far does each data point vary on average? So to find the average, think about what we do. We add up our terms, and then we divide by how many terms there are, which is exactly what we're about to do. So what we do is we have to take each data point in here and find out how far it is from the mean. So we would do that point from the mean, that point from the mean, that point from the mean, and these over here also. All right, so when you do that, when you're finding how far away something is from another point, you're subtracting. So if you look at our formula right here, that's what I'm doing. I'm taking each point and subtracting the mean from it. That's 5. You know, if that were 7 and the mean was 5, 7 minus 5, 8 minus 5, 10 minus 5. Over here would be negative numbers. So, or maybe 2 minus 5, 1 minus 5, 0 minus 5, stuff like that. So remember how you find the average. We're looking for the average distance away each point is from the mean. So the way you find the average is this is how we found the average last week. Remember that sigma means sum. So what we do is we'd add up all of our differences and divide it by how many numbers are in the data set. And that would be our average deviation, or the average of how far away things are from the mean. Now, the problem with that is if I do this on this side, like that may be 7 minus 5, 8 minus 5, 10 minus 5, which are all good. Those are positive. But over here, it'd be 3 minus 5, 2 minus 5, 1 minus 5, which are all negative. And so what would happen if I added up my positive and my negatives, I would get 0 on the top, which means even when I did my division, I would still get 0, which means my variance would be 0. There's no deviation from the mean at all. So what we need to do to take that into account, that there would be 0, is when we do our differences, we're going to square each one, because when you square something, it always becomes positive. So that's how we're going to do that. So really, I'm not getting the true average deviation. I'm getting the squared average deviation, which is a big deal. Now, a couple of things you need to know here. If my deviation, if I end up doing all those calculations and I get a really big number or fairly big number, the bigger the number, the more data, the more spread out the data. If I get a small number, that means there's not very much spread. So in that last slide where we looked at the cookies, the Chips Ahoy variance would be pretty large, whereas the Triola would be very small because one was more spread out than the other. All right, here's the official symbols for variances. The symbol we use for variance is lowercase sigma. That's lowercase sigma. It's kind of a cross between a cursive O and a cursive V. And it goes with the square, symbolizing that we squared the numbers inside when we found the differences. Also notice that because it's population, I use mu for the mean because that means population mean. And a big N on the bottom, capital N, means population, the whole entire population. So when you see the symbol, the sigma squared, that means the population variance. If you just see S squared, that means it's a sample variance. And the only difference in the formula really, it's still squared also, but I'm using X bar because that's the sample mean. And on the bottom, I'm using N minus 1. Now, to figure that out while we're using N minus 1, that really goes beyond what we're going to do in this class. More advanced statistics will teach you that, but we're going to kind of stick with the fact that it's just a little bit different. It's because it's a sample. And that's the main reason I'm just going to tell you for today. It's because it's a sample and not the whole population. And 9 times out of 10, we're going to be using the second one because most times we don't know the whole population. We don't know every number in the population. We usually take samples of the population. So that's what we're going to be using is N minus 1 the most. And again, what the variance tells you is what the average squared distance is to the mean. Now, that's pretty interesting, and that does get you some data. You know, it gives you a number, but even better than that is on the next slide. The standard deviation. The standard deviation is basically the square root of the variance, which means instead of getting the squared average, you're really getting the true average, because if you square something and then you take the square root, what you did, you made it positive, and then you took the square root back. I mean, you took the square off of it. That's what happens when you take the square root of something that's squared. So the standard deviation is the main one we're going to use. We're going to use variance that much. We're going to use the standard deviation. We're going to find the variance and then take the square root of it. And this really truly gives you the average, the best we can do. A data value is from the mean. The average of each point in the data set. What's the average? How far is the average data point from the mean? Little s will be the sample standard deviation. Little sigma will be the population standard deviation. Notice there's no squares on these because we took the square root. They're the real sample or the real average. Okay, I put one example on here. I put these numbers. That's our data set, real small because I want to make the calculation too very long for us. 2, 4, 6, 8. First thing I did is found the mean. I added them up, divided by 4. And I got 20 divided by 4, so my mu is 5. And the reason I'm using mu is because that's the whole population. That's all the numbers, 2, 4, 6, 8. So first thing I'm going to do, that's the formula for standard deviation because it has a square root. Without the square root, remember, it's the variance. And I'm using n on the bottom and mu because it's a population, not n minus 1. And so what I do is I take each number in here, every single number, subtract it from the mean, subtract it from the mean, subtract the mean. I should be saying subtract the mean from it. And then square each value. And when I squared them, I subtracted and squared. I got 9, 1, 1, 9, all divided by 4 because it was 4 numbers. Work that out. On the top, I got 20. On the bottom is 4. 20 divided by 4 is 5. So really, 5 would be the variance. But like they're not 5 apart up here. The mean is 5. It's right in the middle. So I take the square root of 5. So that I got 2.23, which tells me the average number is 2.23 away. The average distance, each data value is 2.23 away from the mean. That's the average distance. Not really huge, so that data set is not very spread out. So my number is relatively small, being 2.23. All right, five or six properties right here of standard deviations you need to be aware of. First of all, this is what it is. The definition is a measure of how much data values deviate away from the mean. How far they average being away from the mean. The value's almost always positive. The only time it is not positive is sometimes it is 0 if all the data values are the same. Like if the whole data value is 4, 4, 4, 4, 4, 4, 4, none of them deviate. The mean is 4, all the numbers are 4. There's no deviation from the mean. It cannot be negative. Standard deviation is never negative. Larger values indicate greater amounts of variation. The bigger the number, the wider the spread. The value of a standard deviation can increase dramatically if you put outliers in there. Because think about it, outliers spread the data out. And the further away the data gets spread out, the bigger the standard deviation. So it's going to increase big time. The units of standard deviation, such as minutes, feet, pounds, whatever, are the same as original data. That's what else makes it good. When you do variance, we didn't talk about this, but variance gives you the square of those. So if you're working in feet or whatever, and you do the variance, you're getting feet squared because you're squaring everything to do the variance. That's why standard deviation is so much better, because you're taking the square root of it, but getting rid of the squares and just finding a true average. The sample standard deviation is a biased estimator of the population standard deviation, which means using the sample standard deviation to estimate what the population standard deviation is not a good way to do it. It's very biased. And we'll talk more about that as the year goes on. But to be honest, a sample mean is a good estimator. Sample mean usually is about the same as the population mean, but the sample standard deviation is not always the same as the population standard deviation, so it's not a great estimator. All right, I try to talk through that fairly quickly because it's so important. Please, please, please take good notes. And this is just an important concept, and it's really important that you understand it, what it's talking about, even more so than the calculation. We'll work on the calculation part in class, but you need to make sure you understand what we're talking about. So I hope that helped. Watch it again if you need to, and again, however many it takes. But we got to get this. So I'll see you in class tomorrow. See you, bye.